Hi, this is a video on U substitution. U substitution is a way in which we can do indefinite and definite integrals, and it is used especially to undo a chain rule. So let's see how it goes. We have composite functions, right? We know about these from the fall. Composite functions are going to be those functions that are differentiated using the chain rule. And so we know that an indefinite integral is an antiderivative, so we have to undo a differentiation, and we can find the antiderivative by this technique called U substitution, which kind of undoes a chain rule. So let's see how that works. Here, for example, is an example of a chain rule, first of all, being applied here to an outside, in yellow, inside, right? So we've got a composite function like f of g of x, or out of in, right? Out of in. That's the composite function. When we take the derivative, we know this becomes f prime of g times g prime of x, and we say out prime of in times in prime, right? And that's the derivative. Okay. So now when we take an antiderivative, we're just going the other way. So an antiderivative of this whole thing right here, this whole thing in green, right, would be the sine x squared, right? So that's what this equation here says. The antiderivative of this whole equation comes back to the thing we started with, or sine of x squared. So this is the kind of situation, this red integral here is the kind of thing that we are going to use a U substitution for. Here, I differentiated first, and then I undifferentiated or took an integral. So you clearly saw that the integral of cosine x squared 2x is equal to sine of x squared, right? But normally you may not be able to see that just looking at an integral, and this is where the U substitution is going to come in handy. So in general, if we have a differentiable function and u is equal to g of x, then we can take the integral of f of g of x times g prime of x by using a U substitution. So we're going to substitute this inside function and call it u. And so then if we think of the derivative, which is if you think of du dx, right? Well, u is just g of x, right? U is equal to g of x. So du dx would be g prime of x. And so you can see that this term in here, g prime of x dx, is nothing other than gu. If we just cross multiply du, I'm sorry, not gu. If we cross multiply here, du is equal to g prime of x dx, right? So I can replace this whole thing with this, and I've transformed my integral into an integral in the variable u. And then all that I need to do is find the antiderivative of this outside function, and that would be the big F. And I now have my answer to the original problem. At the end, we're going to come back and put in the g of x that we initially substituted with u. So let's just do an example to see how this works. So here we have an integral, and the answer to this, it's an indefinite integral. The answer is going to be a function. I'm going to look for a composite type of structure, right? And I'm seeing this inside function, and then the outside function would be all of the rest of that maybe, right? So I'm going to take that inside function and call it u. So I can start by just doing that. U, this is our step one. U is equal to 3x cubed minus 50. That's going to be step one. Step two is going to be to do du dx. Du dx is 9x squared. Now, I'm going to solve for dx by cross multiplying. So dx is going to be du divided by 9x squared. And we're going to treat these du and dx like they can be separated. So when we separate them, usually we left it as, dy dx or du dx, and that was just one thing. But we can also separate them, and when we separate them, those are called differentials, right? So du and dx are called differentials. And we treat them kind of like it's just a fraction. So the du over, just treat it as du over dx, and then you cross multiply and divide by the 9x squared to get dx is equal to du over 9x squared. Okay, then step 3 is going to be to rewrite my integral. So rewrite integral using u and du. You want to end up just with u and du in your integral. So in this case, I come back here and I take the green thing, and the whole green thing is equal to u. So I'm going to call that u, and then I have u to the 20. And on the out here, I still have this 2x squared. I'm going to leave that in for a moment. And I'm going to put dx from here, right, back in there. So dx is du over 9x squared. So I'll just put that in. And now you'll see that what happens here is the x squared is going to cancel. And now I do have an integral 2u to the 20 du, which is just a function of u and du. There's no x's in there. So now this is in the box we have arrived at this stage, right? We have written the function as a function of u du. And now you're going to see that we can actually take this antiderivative. We can just pull the 2 through the integral because a constant multiplier can just come out. And then antiderivative of u to the 20 is u to the 21 over 21 plus c. So I have my answer. So I guess step 4 will be to find the antiderivative, which I just did. And then step 5 will be to rewrite the function using x. So we're going to put back the u substitution that we made earlier. And we said that this was 3x cubed minus 50. U is 3x cubed minus 50. So I'll put that back in, and this will be my final answer. Oh, and I think I lost a 9 along the way. Yeah, I lost this 9. So I'm going to add that in here as a constant. So really I'll have 9 times 21, or 189 down there, and that will be my answer. Okay, let's do this example. So here I see my problem. I see a composite function, so I'm going to think I will need usually a u substitution for that. I will call the inside function u. Step 2 is du dx. Du dx is 2. Dx is equal to du divided by 2. So I'll come back here and write this integral as rad u du divided by 2. That's step 3. Rewrite the integral as f of u du. Step 4 is to find the antiderivative. So now I'm back to scales and arpeggios, or knowing how to do antiderivatives. So this antiderivative becomes that, and I know that this is just 2/3 u to the 3/2 plus c. So I'm ending up with 1/3 u to the 3/2 plus c, and step 5 will be rewrite as f of x, big F, because I've taken an antiderivative. So 1/3 2x plus 1 to the 3/2 plus c. Okay, I want to show you a special case of u substitution where we do see a composite function, but the integral is going to boil down to something we can do more easily than needing a whole u substitution. I'm going to show you the u substitution and have you notice that the du dx is equal to 1. In other words, du is equal to dx. And when that happens, let's do the u substitution and see what happens. This just boils down to square root u du. And that is the same as integral u to the 1/2 du, which is 2/3 u to the 3/2 plus c, right? And so that is 2/3 x plus 1, the quantity to the 3/2 plus c. That's my answer. Now notice that if I had just taken this function and kind of done a reverse power rule on the whole glob, right? The glob is the square root of x. The glob is this x plus 1, right? So I'll just treat that like a whole glob, or a thing that has to be kept together, and I'll do the reverse power rule on that. And I would get add 1 to the power, so that's, now I take that whole glob to the 3/2, right, times 2/3. And so I get that answer by doing the reverse power rule to the whole inside function. So when the inside function has a slope of 1, right, or in other words, when du is equal to dx, we can just do the reverse power rule or the antiderivative or whatever it is of the inside function of the outside function, and we'll get our answer. You know, another example might be like if it were cosine of x plus 5, you know, dx. Then this one, again, I'm noticing an inside function with a slope of 1. So the antiderivative will just be sine of x plus 5 plus c. You can do the u substitution, but you'll save yourself some time if you recognize this trick. Okay, example 3 is here. So my inside function u is 1 minus 4x squared. Du dx is equal to negative 8x. dx is equal to negative du divided by negative 8x. Rewriting the integral becomes x is still there, square root of u on the bottom, du over negative 8x. The x's are going to cancel, which is what I want, because now my integral is entirely in terms of u, and I'm back to scales and arpeggios. I know how to do this integral very easily. This is 2u to the 1/2 plus c. And last step, substitute the u. So 2 times 1 minus 4x squared to the 1/2 plus c. And if you want to write that as a square root, you can do that as well. And there's your answer. Example 4, trig function. Trig functions, it's the inside again, which is the angle here, this angle of the trig function. That's what you're going to use as your u. So u is equal to x to the 4th plus 2. du dx is equal to 4x cubed. dx is equal to du divided by 4x cubed. Come back into the integral, cosine of u times x cubed times du over 4x cubed. The x cubed cancel. And now I have the integral of 1/4 cosine u du. The 1/4 comes out, and the antiderivative of cosine is sine plus c. So final answer, 1/4 sine of x to the 4th plus 2 plus c. Example 5, exponential. When you have an exponential, the power is that is the inside function, and that power is what you should usually call u. So u is going to be equal to rad x. Du dx, as we know from before, is 1 over 2 rad x. dx is equal to 2 rad x du. Let's come back in here and rewrite the integral of e to the u over rad x times 2 rad x du. Rad x's go away. Antiderivative of 2e to the u is 2e to the u plus c, and replacing my u as rad x, I have my final answer. And with all of these, you know, you can take this answer, for example, and let's take a derivative. The derivative would be by the chain rule, 2e to the rad x times 1 over 2 rad x. 2's are going to cancel, and I'm left with e to the rad x over rad x, which is precisely the integrand here, right? So that's the meaning of an antiderivative, right? Okay, tan 3x. This one, I mean, you are seeing a composite function, but notice with all the other ones, I mean, there was the composite function, but then there was something else as well, right? Here, for example, here's my composite function, and then there was something else. Something else which is very much related to the in prime, right? Here, when you see this, there is a composite function, but then there's nothing else like related to the in prime sitting there, right? So how can we do this? Well, we can think of tan as the integral of, sine over cosine, right? So I could rewrite this as sine 3x over cosine 3x. And now we can see that, you know, I could say u is equal to cosine 3x, for example, and then du dx. This is a little bit of an exception, you know, because I'm not saying that 3x is the inside function. Like if you're wondering back here, why didn't we do that? You know, you can do that, but the problem is it doesn't really get you anywhere, because if you say u is equal to 3x, then du is equal to 3 dx, and I guess you're going to end up with something like this, right, which doesn't help you to solve the problem. So then you have to think about, what else could I do? Well, another thing we could do is try to rewrite the tangent and see where that gets us. So I could do this, and now you might again be saying, well, how do I know, whether to choose this as my u or the sine as my u? And all I can say is that it's a bit of an art. It takes practice to cleverly define u so that you can actually do the transformed integral. So you just try things. So du dx here is negative 3 sine 3x. So then dx is equal to du over negative 3 sine 3x. And then I can come back here and say, okay, well, now I've succeeded in saying there's a u down here, there's a sine 3x still up here, and the dx is du over negative 3 sine 3x. So this is looking promising because these will cancel out, and I'll have integral of du over negative 3u, which, remember, this is the same as negative 1/3 du over u. Or, this always confuses students, so I'm trying to say this different ways. This is the same thing as this, negative 1/3 times 1 over u times du. So the negative 1/3 can come straight out, and the 1 over u becomes ln of the absolute value of u when you take the antiderivative, right, plus c. So my final answer here will be negative 1/3 ln of cosine 3x absolute value plus c. Okay, second part of the lesson is evaluating definite integrals using u substitution. So remember, the answer to a definite integral is a number. And the thing we need to keep in mind with the u substitution is that the number has to be correct, of course. And so we need to change the limits. We need to change the limits when we do a u substitution. So what do I mean by that? What I mean by that is this. Here's a u substitution problem. I see my inside function here, so u is equal to x squared plus 1. I see something related to the in prime out there, so du dx is equal to 2x, right? And dx is equal to du over 2x, and I can see that when I put that in, the x's are going to cancel. So, everything is looking pretty nice. Let's just do it, in fact. It's looking like this, which is all great. We're all happy. The only thing is we have to change these numbers, right? So what we do is we say, I like to write on the side, when x is equal to 1, u is equal to 1 squared plus 1. So plug it into the u equation. When x is equal to 2, u is equal to 2 squared plus 1, which is, 3. X is equal to 3 up top. So x equal to 3, this is equal to 10. 9 plus 1. So now my integral in u has to be written as going from 2 to 10, not 1 to 3. And that's super important. So now I get u cubed over 2 from 2 to 10 du. And so my antiderivative is 1/2 u to the 4th over 4 going from 2 to 10. And that is 1/8. And recognize that you can pull this out when you're doing the subtraction of the top and the bottom. So 1/8 10 to the 4 minus 2 to the 4. And I think this answer, you don't have to simplify that without a calculator, but I'll just do it for you. Here it's 1248. And that's the area. Recognize definite integral is an area. So this is the area, net area between this graph and the x-axis going from 1 to 3. Okay, example 7, same type of idea. So we're going to practice changing those limits. U is the inside function. Du dx is negative 5. Dx is du over negative 5. Coming back here, don't put the limits on, but we can do all the other stuff. I have u squared on the bottom. And dx is du divided by negative 5. So I have something like this, and then x is equal to 1, u is equal to 3 minus 5 times 1, which is negative 2. When x is equal to 2, the upper limit, then u is equal to 3 minus 5 times 2, which is 3 minus 10, or negative 7. So my integral is going from -2 on the bottom to -7. So notice, guys, this integral, the x integral, was going from left to right, right? Because 1 is before 2. This u integral is going from -2 to -7. It's going from right to left because -7 is less than -2. But you do not need to do anything other than proceed and do the correct math here. Don't be switching things around or adding negative signs. You just put the numbers in as they come out. When x was 1, u is -2. This is a lower limit, so you put it on the bottom. Lower limit of integration. This right here is the upper limit. U is -7. You put that at the top, right? So keep all of that just the way it is. Now you're going to get -1/5 and then integral of u to the -2 du, which is equal to, and then -2 and -7. Please pay attention to your notation. Math is really not math without proper notation. So pay attention, write the integral, say it's equal to the antiderivative, adding 1, right? And then dividing by that -1, which basically makes the -1/5 positive, and then going from -2 to -7. And then at this point, it might be nice to like put this with a positive exponent. It might just help you do the rest of this more correctly. So 1 over -35 minus 1 over -10 would be my answer here. So that's going to look like 1/10 minus 1 over 35, which is going to be, you can simplify this. We'll say it's a common denominator, I guess, of 70, and it'll be 7 minus 2, which is 5 over 70, and that's 1 over 14. That's my final answer. Okay, let's take a look at this guy. So here again, it's one of those where you don't really see an obvious composite function, but you do see an ln x, and you do see its derivative, right? Remember this, look, this is written like this, but it means the same as ln x times 1 over x times dx, right? So we're seeing a derivative in the integrand, and that's another kind of cue for a u substitution, right? So we can say u is equal to ln x, du dx is equal to 1 over x, okay? And let's see where that gets us. Also, dx is equal to x du. So integral u 1 over x, x du, so this cancels out. So that looks great. Now the limits, when x is equal to 1, u is equal to ln of 1, which is 0. So 0 goes on the bottom. When x is equal to e, u is equal to ln of e, which is 1. 1 goes on the top. So now I've made my integral 0 to 1 u du, super easy integral, and I have an answer of 1/2, right? So 1/2 is the numerical answer that we expect out of a definite integral here, okay? Okay, one last little topic which we've already mentioned, but I wanted to write it down for you, is we can sometimes use symmetry to simplify the evaluation of a definite integral. If f of x is even, then f of -x equals f of x, and the integral from -a to a will be the same as twice the integral from 0 to a. If f is odd, then f of -x is equal to -f of x, and then the integral from -a to a of f of x dx will be 0, right? And I gave you in class the example of the cosine function, which is even. That looks like that, right? And you can fold it across the y-axis, so it's even. So what we're saying is that if you're integrating from, say here to here on the cosine function, you can just integrate from here to here, this yellow piece from 0 to pi over 2, and double that, okay, because the function is symmetric. Sine function is an odd function, right? So the sine function looks like this, and then on the other side it looks like this, right? So for the sine function, if you're integrating from here to here, right, those two areas are going to cancel out, okay? And that would happen if you were going, from negative pi over 6 to positive pi over 6, right? That would be these little areas here, but they would be symmetric, so they would cancel out. So sometimes when you look at an integral and you don't have a way of finding the antiderivative, think if you can use symmetry to simplify your life. This right here, x to the 6 plus 1, that I believe is an even function. Let's check. F of negative x is equal to negative x to the 6 plus 1, which is the same as x to the 6 plus 1. So this is even, right? So I can do this integral by just saying this is equal to 2 times the integral from 0 to 2 of x to the 6 plus 1 dx, right? And I'm not going to finish it out because the point is just to show you that. This one right here, again, look at these limits, these symmetric around 0. And so you look at this thing in here and I have no idea how to find an antiderivative of that or to graph a shape for that. So I'm going to think about symmetry, and I'm going to think, let me try f of negative x, right? F of negative x is tangent negative x over 1 plus negative x squared plus negative x to the 4th. This bottom piece is just going to be 1 plus x squared plus x to the 4th, and the top tangent of negative x is negative tangent of x. How do I know? Well, because I know that the tangent graph, which you know from pre-calc and algebra, looks like this, right? So I know that, for example, tangent of pi over 4 is 1, but tangent of negative pi over 4 is negative 1, right? So that's why I can say tangent of negative x, tangent of negative pi over 4, for example, is negative tangent of pi over 4, right? It's equal to negative 1. So anyway, I can see that f of negative x is equal to negative f of x, and that's the sign of an odd function. So I can decide that this scary looking integral is equal to 0, because if I'm integrating an odd function across limits that are symmetric on the two sides of 0, those are a net, the integral is a net area, right? Definite integral is a net area, so those are going to cancel out. Okay, takeaways. Use U substitution when the integrand, pause the video and do them, and then check what I'm saying. Use U substitution when the integrand is a composite function f of g of x and g prime of x, the derivative of the inside, is somehow present in the integrand. If the inside function has a slope of 1, U substitution is not necessary, right? This is that case I was telling you where du is equal to dx. So here we see an inside function, but the du will be equal to the dx. So I can just go, this is just sine of x plus 5, plus c. Okay. For U sub with trig functions, try u is equal to the angle, right? What do I mean by that? I mean if it's cosine of x squared plus 2, this right here is the angle inside the cosine function. So again, it's the inside function that we're using. And for U sub with power functions, try u is equal to the power, right? Which is again the inside function. The power, what do I mean by that? It's like that e to the rad x problem, right? This power, it's the inside function. And we're going to try to use that as u. For U sub with definite integrals, remember to change the limits of integration, change the numbers on the top and the bottom of the integral. When you see an integral that looks like negative a number and positive a number as the limits, so you know you're going on two symmetric sides of 0, right? Think of symmetry, because you might be able to use that to simplify your integral. And I hope that was a useful video to you. I can't wait to see you next time. And have fun with U substitution.